Hello, differential equation students. Topic 13, second order linear homogeneous ordinary differential equations with constant coefficients. In this section, we devise a strategy for finding solutions to these kinds of ODEs. Right here, we are seeing that the second order linear homogeneous differential equation can be written in this way. We have y double prime isolated plus some coefficient function of x times y prime plus some coefficient of x, function of x times y, is equal to 0. The fact that it's linear is the fact that we have these terms being able to express this way, and what makes it homogeneous is that we have a 0 function on the other side. Now specifically, we're going to talk about a strategy for solving such differential equations, but where the coefficients are constants. They are not functions of x. So I've changed the p of x to a simple p and the q of x to a simple q to indicate that they are now constants. We're going to devise the strategy, and I'm going to demonstrate it right here for this particular second order ODE with constant coefficients. That is also homogeneous, and we're going to find the particular solution that satisfies this given data right here. Okay, so let's begin by assuming that the solution to this differential equation will have a certain form. And we're going to assume that that form, so we'll say assumed solution has the form y is equal to e raised to some constant. I'm going to put a lambda there, that's a Greek letter lambda, times t. And we are going to differentiate this once and then twice, substitute it into this differential equation, and figure out what lambda has to be so that the differential equation is satisfied. So let's find out what the first derivative would be. If y is equal to e to the lambda t, and by the way, lambda is the Greek letter, it's spelled this way, this is what I'm saying, lambda. And the first derivative would be e to a constant times c. Lambda we're assuming is a constant, so the derivative using the chain rule would be lambda times e to the lambda t. You want to get practice doing some lambdas. They can sometimes look like 2's, like if you do a 2 like this, or sometimes lambdas start to look like 2's. It can be confusing, so learn how to write a lambda. I do a little mark like this and then put a little foot on the bottom of it, and there's our lambda. You're going to get some practice writing lambdas in this unit. Second derivative would be, the chain rule again would produce another lambda, so it would be lambda squared would be the coefficient times e to the lambda t. And here's our function and its first two derivatives. Now we're going to substitute into this differential equation and see what happens. So the second derivative we can replace with lambda squared e to the lambda t plus 2 times the first derivative, which was just lambda times e to the lambda t, minus 8 times the original function, which is just e to the lambda t, is equal to 0. Now notice that we can factor out the e to the lambda t, and that leaves lambda squared plus 2 lambda minus 8 is equal to 0. And we want to find all values of lambda that make this a true statement. Now the first part of our factoring, this e to the lambda t, either that's equal to 0 or this second factor is equal to 0. But the first factor is an exponential, and e to the lambda t can never be 0 no matter what lambda or t are. E to a number is always going to be positive, so it won't contribute to the solution of this system. So instead I'm going to set this quadratic in terms of lambda equal to 0. And so this is what we want to solve for lambda. Lambda squared plus 2 times lambda minus 8 is equal to 0. Now, as far as terminology is concerned, this entire equation here is called the characteristic, or sometimes called the auxiliary equation. And the polynomial just on the side of it is called the characteristic, or the auxiliary polynomial. You'll see those terms later in our notes, so I won't write them right now. Now, solving this quadratic equation, turns out this one factors, so we can factor this by saying x plus 4 times times lambda minus 2 is equal to 0, and we get two answers. Lambda could be negative 4 or 2. And let me move this work over here just slightly. These are the two values of lambda that would create a true differential equation, a differential equation that is satisfied. Therefore, we get two different possible solutions. And because one solution is going to be e to the negative 4t, the other solution is going to be e to the 2t, and we can show that those are linearly independent, meaning that one is not a multiple of the other. Therefore, we found two linearly independent solutions to this differential equation. Thus, we can create a general solution by combining them with constants. So our general solution is going to be c1 times e to the first lambda, which is negative 4, times t, plus another constant we'll call c2 times e to the next lambda, which is 2t. And here's our general solution. To find a particular solution, now we just have to find the first derivative of our general solution, and that combined with the original, and plug in this data, and then solve for c1 and c2. So let's first I'm going to rewrite, I'm going to just copy this here, paste it up here so we have it stacked underneath right above the derivative. So there's the original there's a general solution. Now the first derivative, chain rule, would be negative 4c1, and don't absorb this and create a new c, because then you'll have a c3. We want to keep it in terms of c1, so say negative 4 times c1, e to the negative 4t, plus 2c2 e to the 2t. Then here's the first derivative. Oops, y prime, there we go. Now I'm going to plug in 0 for t. I'm going to do the first equation right here, plug in 0 for t, and 2 for y to satisfy this data point right there. So we get 2 is equal to, and if I plug in 0 for t, I'm just going to get c1 times e to the 0, which is times 1, plus c2 times e to the 0, which is just times 1. And now I'm going to plug in a 0 for t. I'm going to use this bit of data right here, that y prime of 0 is 0. So that means 0 is going to go in for t right into this equation right here, and then y prime will also be 0. So we have 0 is equal to negative 4c1 plus 2c2, because the e to the 0s will go to 1s. So I don't need to write them. This creates a system of equations now that we want to solve in order to find what c1 and c2 are. And you can use substitution methods, elimination methods. There's really lots of different options. By substitution, I mean solve this first equation for c1 and then plug that in for the second equation and then solve for c2. And once you have c2, you can go back and find c1. I'm going to do elimination. So I'm going to actually multiply. I want the c1s to cancel, so I'm going to multiply the first equation here by 4, both sides of it. And that turns that first equation into, let's rewrite this, we have 8 is equal to 4c1 plus 4c2. And then the second equation is 0 is equal to negative 4c1, oops, I forgot my 1 there, plus 2c2. And so when you add the two equations together now, that creates a new equation that gives me what c1 and c2, or c2 is going to be. So I get 8 is equal to 6c2, so 4/3 is equal to c2. And then once you know that c2 is 4/3, you want to plug in 4/3 into any of the equations above, really. I can plug c2 equals 4/3 right here, and then subtract 4/3 from 6/3 and get c1 as 2/3. So there are our two constants, and this allows me now to write my particular solution. Let me move this up just slightly, and let's put a particular solution now. Y is equal to c1, which is 2/3, times e to the negative 4t, plus c2, which is 4/3, times e to the 2t. Okay. And this will be the basic strategy we do for solving all of the differential equations we're going to see today. And what's going to cause our variety will be the kinds of solutions we get when I set the characteristic polynomial equal to 0 and solve for the different lambdas. Like what will happen if I get imaginary lambdas, etc. Let's move on to the next example. Following the same thing, we're going to assume that y equals e to the lambda t is going to be a solution to the differential equation that's presented right here, which means that y prime is going to be lambda e to the lambda t, and y double prime is going to be lambda squared e to the lambda t. Now we substitute these into the differential equation. That's right here. And that gives me lambda squared e to the lambda t, that's my y double prime, plus 2 times y prime, so 2 times lambda e to the lambda t, and then plus just y, so plus e to the lambda t. E to the lambda t, there we go, is equal to 0. Again, you can factor out the e to the lambda t's, leaving your characteristic polynomial behind. So 2 lambda squared plus 2 lambda plus 1 is equal to 0. And then that's what we want to solve. Lambda squared plus 2 lambda plus 1 is equal to 0. Now this does factor into lambda plus 1 times another lambda plus 1, so it's really a perfect square. So we only get one distinct answer out of this, lambda equals -1. Now when this happens, your general solution will be the following. It's going to be equal to y, or y is equal to some constant times e to the lambda t, so lambda is -1, so negative t will be our exponent, plus, and then we need a linearly independent second solution. And it turns out that if we do a second e to the negative t, but put a t in front of it as part of the coefficient, this we can show will also be a solution to the differential equation. I leave it to you to verify that. Like, let t times e to the negative t be your y, and then see if in fact this winds up satisfying the differential equation here. And you can show that it is a solution to the differential equation, which means that, and it's also, this is linearly independent from this, therefore combining them with constants in front form the general solution. Another thing I want to point out here is, notice how easy it would be to go straight to the characteristic equation from the differential equation. Right? When you compare these side by side, these two equations, all you really do is just change the y's. If it's a y double prime, you change it to a lambda squared. A y prime, you change to lambda, and the y's, you just change to 1. And you can create pretty easily the characteristic equation. Right? That was also true right here when you look at these two, compare these two lines. The y double primes become lambda squares, the y primes become lambdas, and the y's become 1s. Okay, so now we have a general. So the next thing I'm going to do is find the first derivative. The first derivative will be negative c1 e to the negative t. And for this next one, we're going to have to do a chain rule, or sorry, a product rule, c2 times, and then do the product rule to differentiate this. So we have the derivative of t, which is 1 times the second, plus the first, which is t, times the derivative of e to the negative t, which is e to the negative t times the negative 1. So I'm going to make that subtraction. And here is our y and our y prime. Now we are going to plug in the data and see if we can find out what the constants need to be. So let's first do the first bit of data. Y of 0 equals 4. So I'm going to use this equation right here, change the t's to 0. At the same time, I change y to 4. So I get 4 is equal to c1 plus, and I'm going to get a 0 times c2 over there. So it's just a 0. So this tells me c1 right away. And now for the second bit of data, which is the y prime of 0 equals -2, will be plugged into our derivative right here. All the t's will become 0, and the y prime will become -2. So you have -2 is equal to negative c1 plus c2 times, now keep in mind that t is becoming 0, so this part here is going to go away to 0. This will become a 1, e to the 0 will be a 1, so we just get c2. c2 times 1 is just c2. Now since c1 is 4, well, you could also add these equations together right now and get 2 is equal to c2, because the c1s are set up to cancel automatically. And we also know that c1, of course, is 4, so we can create our particular solution. Y is equal to c1, which is 4, times e to the negative t, plus c2, which is 2, times t, e to the negative t. I'll leave it to you to verify that this function does in fact satisfy the differential equation and both initial conditions. Okay, going to the next slide. Solve the ODE with initial conditions below. Y double prime plus 9y is equal to 0. Okay, let's do the practice where I go straight to the characteristic polynomial. So any y double primes will become lambda squares, and all the y's will become 1. Notice there's no y primes here, so no lambdas. So it's just going to be 9 lambda squared plus 9 is equal to 0 is what we're trying to solve. This is our characteristic equation. Now let's just verify that this does in fact happen, that our shortcut is working. So if we assume that y equals e to the lambda t is going to be a solution, then y prime will be lambda e to the lambda t, and y double prime will be lambda squared e to the lambda t. Substituting these into the differential equation, we would get lambda squared e to the lambda t plus 9 times e to the lambda t is equal to 0. Factor out the e to the lambda t. That gives me lambda squared plus 9 is equal to 0. And sure enough, all that matters, since this first factor can't be 0, so it has to be true that this factor is 0. So we do get our characteristic polynomial as expected. From here on out, I'm just going to do the shortcut. I'm going to go straight from differential equation straight to characteristic polynomial. Lambda squared plus 9 is equal to 0. What are the solutions to this? Well, this does not have real solutions. It has imaginary solutions. Lambda squared equals negative 9. Therefore, lambda could be plus or minus 3i. So our solutions would be of the form e raised to the plus or minus 3i times t. Now we're going to use something called Euler's identity. Let me summarize Euler's identity over here. It's e to the I theta is equal to cosine theta plus I sine theta. This is something that's learned in a trig class that we are going to be using right here. It's called Euler's identity, or Euler's formula. And we're going to use that right here, where the theta is going to be the plus or minus 3 times t. So there's our e to the I theta. And since cosine is an even function, if I put plus or minus the same angle right here, cosine of plus or minus theta is just the same thing as cosine theta. But sine of plus or minus theta, sine's an odd function. Sine of negative theta is the negative sine of theta. So what this winds up becoming is that e to the plus or minus 3it can be rewritten as the cosine of 3t plus or minus I times the sine of 3t. And this is Euler's identity, or Euler's formula. This tells me that when you have e to an imaginary number, purely imaginary number, then it can be decomposed into a combination of sines and cosines. So this is going to allow me to write a general solution in the following way. Our first component of the general solution will be c1 times, and we just take this first part, this function here, this trig function, cosine of 3t, plus, and then some other constant times, and we can ignore the I coefficient because we're after the functions themselves. Sine 3t will be a second function that's going to be a solution to this differential equation. Now these are not surprising answers. I mean, I could have had you just think through derivatives and solve this differential equation right now by, moving the 9y to the other side and saying, hey, what function, when you differentiate it twice, will give you the negative 9 times the original function? And sine 3t and cosine 3t are solutions to that. And they're linearly independent. So when we combine them together with constants, coefficients, unknown constant coefficients, we have the general solution. Now I'm going to want to find the particular solution. So I need to find a derivative of my general solution. I need to get a y prime statement. So the derivative of c1 cosine 3t, its derivative is going to be negative 3c1 sine 3t, right, because the derivative of cosine is negative sine, and chain rule produces the 3. The derivative of c2 sine 3t, chain rule will give me 3c2 cosine 3t. So there's y and y prime. I'm going to take this initial data, y of 0 equals 3, and plug it into my general solution. Change y to 3 at the same time I change t to 0. So cosine of 3 times t, when t is 0, that's going to be cosine of 0, which is 1. So I'm going to get c1 out of this, plus, but sine of 0 is 0, so I'm going to 0 out the second term. The c2 will go away, so c1 has to be 3. And now I'm going to take the second bit of data, y prime of 0 equals negative 2, and plug that into my derivative of my general solution. And y prime will become negative 2. And if you plug in 0 for sine 3t, that's going to 0 out the first term, so that's gone. And when you plug 0 into the second term, you're getting cosine of 0, which is 1, so you just get 3c2. So this tells me that c1 is 3 and c2 is negative 2/3. And now I'm ready to write my particular solution. Y is equal to c1, which is 3, times cosine of 3t, plus c2, so minus 2/3, times sine of 3t. I just rewrote my general solution, but with the correct c1 and c2 in place, and now I have my particular solution. Okay, next example. As you can imagine, we look at the three examples. The second order differential equations are producing second degree characteristic equations. So quadratic equations, which have either two real distinct roots, like we saw here, or they have one real distinct root, like we saw here, and we saw how to create a second linearly independent solution, even if the root is repeated, or they could have imaginary roots. So here we have what's called purely imaginary roots. It's plus or minus 3i. There's no real part, because the normal form of a complex number is a plus bi, where a and b are real numbers. So when the a is 0, you just have bi. So plus or minus 3i is said to be purely imaginary roots. Well, let's see what happens with this case here. All right, the first thing I notice is that I don't like all the decimals, have 0.5s and 2.5s, so I'm going to begin by just doubling the equation and rewriting it. So when I double the equation, double 0.5, you get 1, so we have y double prime plus 2y prime plus, and double 2.5 is 5, so we get plus 5y is equal to 0. It's a little bit easier to solve without all the decimals. Next, I'm going to go straight to the characteristic polynomial. So it's going to be lambda squared plus 2 lambda plus 5 times 1 is equal to 0. And we want to solve this for lambda. And this one, I do not see a way to factor this easily, at least with real numbers. Let's see what happens when I do when I do the quadratic formula. So lambda is equal to negative b, so negative 2 plus or minus square root of b squared, so that's 4, minus 4ac. That's going to be a minus 20 there, all over a 2a, so all over a 2. Let's keep going. Negative 2 plus or minus 4 minus 20 is negative 16, so that's going to produce imaginary numbers. Square root of negative 16 is 4i, all over a 2. And then finally divide everything by 2, so we get negative 1 plus or minus 2i. These are our two lambdas. Notice they're not purely imaginary because they have a non-zero real part, and then plus or minus the imaginary part. So we have a complex number with both imaginary and real parts. So when I say that my solutions, therefore, are going to be of the form e to the lambda, it's going to be plus negative 1 plus or minus 2i times t. There's my e to the lambda t. This is what our solutions are going to look like. One with the plus, one with the minus. But we're going to do a little bit of work here. We're going to distribute the t and write this as e to the negative t plus or minus 2it. Then you can, if you recall rules of exponents, if you have x squared times x cubed, you can write this as x to the 2 plus 3. Or I can do this backwards. So you can, whenever you have an exponent that's a sum, we're going to break it up into a product, like this. So we can write this as e to the negative t times e to the plus or minus 2it. And then I'm going to use Euler's identity on this part right here. So this gives me e to the negative t in the front times cosine of 2t plus or minus I sine 2t. And this is Euler's identity we just used, or Euler's formula. I'll call it identity. I might be using the wrong word there, but you look it up. It's either Euler's formula or Euler's identity. And now I can create my general solution. So the general solution will be y is equal to some constant times, and then it's going to be the e to the negative t times this function here. So e to the negative t times cosine of 2t, and then plus a constant times, and then e to the negative t times this function, the sine function over here. And here we created our general solution. Now it could be advantageous to factor out the e to the negative t if you like, or we can leave it in there. Both of these functions, by these functions, this e to the negative t times cosine 2t and the e to the negative t times sine 2t are linearly independent, so that's why together they form a general solution for our differential equation. We do want to do y prime next. So it's going to be a bunch of product rules here to get this. So we have to use a product rule on this. The c1 will be in the front, and then the derivative of the first is negative e to the negative t times the second, plus the first, which is e to the negative t times the derivative of the second. And chain rule, in derivative cosine, we're going to have negative 2 sine, so I'm going to make this subtract, negative 2 sine 2t, plus, and then let's do the second. We're going to now differentiate this part. Again, using product rule, the c2 in the front. Derivative of the first part is negative e to the negative t times the second, sine 2t, plus the first, e to the negative t times the derivative of sine 2t, which is 2 cosine 2t. So I'm going to move this over, put a 2 in front, and put a cosine of 2t. There's our y and our y prime. Now we're going to plug in our data about y of 0 equals negative 3, about the original function. We're going to plug that into the general solution. The y-coordinate will be negative 3 at the same time that we plug in t equals 0 into the rest of this. Well, t equals 0, e to the 0, so it's going to become 1s. Sine of 0 is gone, that's 0, but cosine of 0 is 1. So we're just going to get c1 out of all this. c1 plus 0. So c1 is negative 3. Now let's plug y prime of 0 equals 1 into our derivative of the general solution right here. Change y prime into 1 at the same time that we change all the t's to 0. So let's see what's going to be left here. That's going to go away because there's a sign of 0 involved. This will become a negative 1 times 1, so negative 1. So negative c1 is what I'm getting out of that. This term here will disappear because sine of 0 is 0. E to the 0 is 1, cosine of 0 is 1, so there's just a 1 here times that 2. And it looks like 2c2 will be what's left. Okay, so we know that c1, if I add the equations together now, I'm going to get negative 2 is equal to 2c2, which means that c2 is negative 1. So I'm going to get c2 is equal to negative 1, and c1 is equal to negative 3. All right, so now we're ready to get our particular solution. And it's really just going to be this. Better see if I can create some room here for us. Put the general solution down a little bit so these don't overlap too much. And we are going to change our c1 and our c2. c1 is negative 3, and c2 is negative 1. So I'm just going to make this be subtract and move this in a little bit closer. And right there is our particular solution. Okay, and that pretty much covers all the possible cases. When you solve a quadratic equation, you're going to get two distinct real numbers, one repeated real number, or two distinct purely imaginary, or two distinct partially imaginary complex solutions. So this takes me to the last slide for this topic, which is summarizing these findings. So complete the table which summarizes the general solutions to second-order linear homogeneous ODEs with constant coefficients. So when your ODE has this form, you can instantly create the characteristic or the auxiliary equation. Right, here are the terms here finally written down. And then depending on the solutions to this equation, that will dictate the general solution of our ODE. So in the first case that we saw in our first example, when the two roots of the auxiliary equation are real and distinct, then our general solution is created by saying y is equal to some constant c1 times e to the first lambda times t, and then plus a second constant c2 times e to the second lambda times t. And this forms the general solution. In the case, like in our second example, when the two lambdas, it turns out that they're repeated, so it's real and indistinct, so there's no I involved, but our general solution will be some constant times e to the lambda 1t plus some constant times t e to the lambda 1t. And so putting that t in front as a coefficient created a second function that's a solution that's also linearly independent from the first one. So this is how you would create your general solution if the lambdas are real and indistinct. Now let's go to the table for entry for when we have a real and an imaginary component. So when a plus or minus bi, where the a and b are not 0. This was actually like our fourth example we did. And when we broke this one apart, if you look back at our last example here, notice that the negative 1, trace this negative 1. Where did that go exactly? That was right there. That created an e to the negative 1 times t, which became a factor in the front, which in the end became coefficients of our two trig functions. And that negative t that you're seeing here and here came because this was a negative 1. If that was a 7, then you would see e to the 7t right there, if you trace all those effects. So what we're seeing here is then if you get a plus or minus bi, our general solution is going to be some constant, c1, times e to the at times the cosine of, and then let's see if we can track what the bi did in this example here. All right, so here's the bi, the plus or minus 2i. Track its effect. That just led to having a doubling of t, and a doubling of t being the two arguments of our cosine and sine functions. So whatever the b is going to be a coefficient of the t's here and here. Okay, so that allows me to say cosine of bt, and then the second term will be c2 times e to the at, that's going to be the same, but then times sine of bt. And this is how we create our general solution. And then finally, the last case is what happens if they're purely imaginary. So you can actually just copy this case here, but just change a to 0 and see what happens. Right? If a is 0, then you're going to have e to the 0 there and an e to the 0 there. Those are going to go away. And your general solution is simply going to be c1 cosine of bt plus c2 times sine of bt. The exponential components will be gone. All right, and that concludes our lesson on topic 13.